Hello there. Welcome again on this fascinating journey of learning research. This is the fourth video of the second chapter. In this video, we'll continue discussing about sampling distribution, and we'll also introduce you to the concept of sampling error. So let's get started. This is where we were discussing in our last video. So we were talking about instead of sampling it once, let's sample it thrice, or let's sample it multiple times. So every time we sample, we arrive at an average, and if we try to plot it, as you could see in this figure, if it is possible for us to go it to have infinite number of samples, we could sample it for infinite number of times, we are more likely to arrive at this kind of distribution, which is actually a bell-shaped distribution, also called a sampling distribution. The point about bell-shaped curve is, in statistics we call it as a normal distribution. So normal distribution is a kind of distribution where most of the data is confined in the central space, and as you move to the extreme, you will get lesser amount of data. So but again, when we talk about sampling distributions, why we the researchers care about sampling distributions? Because in practical sense they could never actually build one. Why? Because to construct one you have to take an infinite number of samples, which is not possible. But then why this sampling distribution is so important for us? Because you just have to appreciate this, that whatever sample you are drawing for the sample from the population is just one of the potential number of samples you could have taken, and there are fair chances that your sample average would also be would be near the center of the sampling distribution. And if on the theoretical note, if we take the average of the sampling distribution, the average of a sampling distribution of infinite number of samples, where do we arrive at? We will definitely arrive at the true population average, because that is what our whole idea is. We wish to actually estimate the population parameter, and that is why this whole exercise of sampling distribution comes into picture. Just to remember that the average of sampling distribution, if somebody asks you what is the average of sampling distribution is actually a distribution of samples. Every sample has its own average, so the average of sampling distribution is actually the average of average, and which is essentially equivalent to the parameter. So that is why sampling distribution is important to us. The next is the concept of standard error. So now, having said about the central value, we are also interested in the spread. So in statistical concepts we have something called standard deviation. So using the same concept of standard deviation, the standard deviation of sampling distribution will tell us how different samples would be distributed. Like you have your different samples, so how these samples are distributed around this mean value, which is actually the average of averages. So this term is referred as the standard error. So just to keep it separating from standard deviation. If we are dealing with raw data, just you have drawn a sample and you definitely it has a mean value and it has a spread, so that would be standard deviation. But if you will refer to the standard deviation of sampling distribution, then it would be called as standard error. So just to make these things clear, the standard deviation is a spread of the scores around the average in a single sample. So in a single sample, in any sample, if you draw, you will always get a mean value and a spread. So data spread is actually measures of dispersion. We always have a standard deviation and we always have a mean. So a specific mean and a specific standard deviation, whereas a standard error is something which we are talking about as a whole, collectively. The spread of averages around the average of averages, right? Sounds little tricky, but hold on, it's quite simple, believe me. In sampling context, the same standard error is called sampling error. So from standard deviation to standard error to sampling error. Okay, so standard deviation is a statistical concept. Same concept when we are applying it in terms of sampling distribution, we are calling it as standard error, and in sampling context we are calling it as sampling error. So one the same, standard error and sampling error are one the same. So what is sampling error? Sampling error gives us some idea about the precision of our statistical estimate. So if we are estimating something about our population parameter, so how good is our population parameter, how well we have estimated? So we normally use statistics to estimate population parameter. So we have a mean, that is the sample value, average, and we also have a standard deviation of a sample standard deviation. So from that we compute sampling error. But then try understanding that sampling distribution is something which we cannot create, because again it will take infinite number of samples to create it. So we normally estimate it. So how do we calculate sampling error? It is simple. We normally base our calculation on the sample's standard deviation, and it depends on two things. One is the greater the sample's standard deviation, we have strong reasons to believe that greater would be the standard error, right? Because there is a much of variability in sample itself. So population is bound to be so whatever it will have a greater standard error as well, because in the sample itself it is clear there is too much of variability, right? So the greater the standard deviation, greater would be the standard error or the sampling error. The next is, the greater your sample size, smaller would be the standard error, because when you try to bring more and more units into your sample space, what you are actually doing, you are actually trying to have a better estimation of the mean of the population. So somewhere you are approaching that. So that is why just in case, imagine that you are able to cover every member of a population in your sample. So what will happen to standard error? Standard error would be 0, because you have actually arrived at the parameter. So that is what I want to say. If your sample size is small, standard error would be great, right? If your sample size is bigger, the smaller would be your standard error. So this is what the next is the application part of it. In any normal curve we have this 65, 95, 99% rule. In some books of statistics it is 68, 95 and 99 point something 99% rule, but yes, in this book we have this 65, 95, 99% rule. So what this thing is all about, and just to give you an estimate, that if we move from central value, if we move one standard deviation from this side and one standard deviation from this side, how much data we have covered? We have covered 65% of data. If we move two standard deviation on both the sides, we have covered how much amount of data? 95% of the data area. And if it is three standard deviation, we have covered 99% of the data. So this builds a very strong logic that if we have some central value and we have a if we know what is the sampling distribution average, and if we know the sampling error, we could clearly estimate what is the population distribution, what is the population parameter. But again, the same thing, that we cannot do that because we do not actually have the sampling distribution. So what is the way out, how we could estimate the sampling error and sampling distribution? So let's try to let me give you an example. Let's say in a study you drew a single sample from the population, and let's say the average of the sample was 3.75 and the standard deviation was 0.25. So let me take you through this. So if this is the case, so 0.25 is your standard deviation and mean value is 3.75. You just have to add 3.75 plus 0.25, you arrive at 4, and if you minus this 3.75 minus 0.25, you arrive at 3.5. So basically whatever values, I mean within this value 3.5 and 4, 65% of the people are there. And following the same logic, we could actually arrive at the extreme scores also, that how much of the sample is between these values. So this gives a very beautiful way of looking into this phenomena. Now coming back to our example, it's okay that we have estimated, we calculated it for sample, but we are actually interested in sampling distribution. But how can we do that? We could really estimate it. The first one is that whatever mean we have calculated from our sample, we treat that mean as the mean of sampling distribution as well. Okay, so the mean of the sample is equal to the sampling distribution mean, so 3.75. This as a starter you have to go like that. Then you have to calculate the standard error. Now standard error, as we know that it depends on two things. One is your sample standard deviation, and the other one is your sample size. So let's say if you have taken sample size of 100 and you have your standard deviation as 0.05, 0.25, So using this n is equal to 100, you will get a standard error of 0.025. So now you have everything. You have a central value which is actually the average standard, the mean value, the mean of the sample, sampling distribution mean. The mean is 3.75, and you also have the standard error which you have actually calculated, 0.025 for n is equal to 100. Okay, right? So this is what your statistics is. N is equal to 100, your sample mean was 3.75, your standard deviation was, so mean value, let me standard deviation was 0.25. So from here you have estimated your sampling error as this. So if you would estimate that the probability of is 65% that the true parameter, let's see, the true parameter falls, what is the probability that the true parameter falls between these two range, 3.725 and 3.775? 65%, right? How you have done it? Same way, the way we have done it earlier. 3.75 minus this value, 1 standard deviation plus minus, 95% confidence, again twice of this value, plus minus, so 3.700 to 3.800, that is the probability. So we started with a mean value and we actually arrived at population parameter. So this is what the power of sampling distribution and sampling error is all about. So how you could do that, how this estimation helps you, sampling distribution helps you to estimate population parameter. I hope you have understood. There are many things to follow, and it is very likely that in the first go you may tend to not fully understand these concepts, but believe me, bear with me for some times. In the upcoming videos these things would be very, very clear. So just have a relook into the logic. The idea is to follow the logic, right? You should not miss the concept that way. Evaluate the concept from the logic. What is the logic which we are trying to build? What is the argument which we are trying to build for sampling distribution? This is this should be clear in your mind. Okay, with these words I'll stop here, and thank you very much. Keep watching.